Essentially, we're working. Good morning. Essentially, we're going to be working today on sampling distributions. There are two main kinds of questions. We've covered a lot of it, so there'll be a little bit overlap. I'm going to look at this again, just another example, just to get us back into the swing. It's how you can use a sample to estimate a population proportion. That's essentially what that one's about. And then the new thing that we're going to be looking at is that if you already know the population proportion, you can use it as a predictor of what you might get from a sample. And you might think, well, I don't think that's going to be very helpful, but sometimes this number 2 can also be helpful. So let's do number 1 again. Right, so I would like to know the answer to a question like, who's going to win the next governor's election, right? So let's say it's in Texas, and we get a sample of 1,000 people, a nice simple random sample. And we ask them, are you going to vote Republican? And you say yes or no. And 550 of them said they were going to vote Republican. So we get 0.55, which of course is 55%. Now, just based on this piece of data, you could say that there's evidence to prove that the Texan is going to win the governor's election, whoever that Texan guy is, the Republican one is. Right? Because if you get 55% of the vote, won't you win the election, right? In fact, to win an election, you only need 50% plus one extra person. But we know that there is a better way to tackle this question. And what we do is we generate an interval. So we calculate this guy, right, the standard error of the sampling distribution, SE of p hat as it's called. And it's a formula that looks something like this. Anybody remember what goes inside the formula for the standard error of p hat?
P times Q.
Okay, so we'll call it p hat times q hat in the context of this question. And something goes in the bottom, doesn't it?
N.
N. So you've got to know that formula. Essentially, p hat is 0.55. The N is the sample, which is in this case 1,000. Whoops, that's my cell phone. This guy here. Oh, what's Q hat? And I know that I mentioned it. I could remember saying it. What is Q or Q hat, depending on the context?
It would be the other half, or the opposite of P.
Yeah, the rest of 1, or whatever way you want to phrase it, right? Now you put this package together, and we get to, well, eventually, I'll get a square root of 0.55 times 0.45, and then I'll divide it by 1,000. And the answer I get in this case is 0.0, I'll round it off to 1.6, which is 1.6%. Now, we have, it's called the empirical rule, the 65, the 95, and the 99.7. Remember those guys? And this one is basically 1 standard deviation, right? Plus or minus 1 standard deviation away from the mean. If you go 2 standard deviations away from the mean, or if you go 3 standard deviations away from the mean. Essentially what these will do, these will give us confidence intervals. So I'm going to pick this one. So a 99.7% confidence interval would be the mean, in this case p hat, plus or minus 3 standard errors. So it would be 0.55 plus 3 lots of this guy. And this would be 0.55 plus 0.048.
Professor Robertson?
And yes.
Where is, I'm lost when you started doing confidence interval. Why did you use 3?
I just decided I wanted 3.
Oh.
The question would that the question would tell you, I want a 95, I want a 99.7. I hope they never ask for a 68, but they do sometimes.
Okay, I see. Thank you.
Right. So I just picked that one. There was no, well, I guess I picked it because I wanted to be as certain as I could be that the interval was pretty much guaranteed, not 100%, but pretty much guaranteed to have the real answer. Now, that ends up being 0.502, and it could be as high as 0.598. And if I convert it into percentages, the predicted percentage of people who are going to vote Republican, right, a 99.7% confidence interval, is this range here. And based on what you're seeing here, isn't every single one of these numbers bigger than 50%? So if this was a poll that was taken just after the polls had closed, right? So people on the way out, they'd voted and they collected it. They would be able to, just on this random sample of 1,000 people, they would be able to say, we predict that Texas has gone Republican. So if you've ever been in the election and you say, but they've only counted 20% of the votes, or they've only done blah, 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 or they've only, they've done an exit poll very often, and yet they're still predicting the winner. And people think, oh, that sounds suspicious. Have they already decided who's going to win? And the vote really didn't matter? No, it's the statistics has clearly found a winner in this question. Now, in a different world, can you imagine that the answer might have been 49.8% up to 54.2%? Can you imagine a different interval came up with that one, right? In this world, couldn't the Republican have lost Texas? Because if he gets that vote, let's assume there are only 2 people, right? If he got that vote, didn't the other guy get 50.2% and he actually won? The Democrat won. Now, when you have an interval like this that has the 50% in it, what they do in the TV, they would say Texas is too close to call. The number that is here, this 4.8%, is called the margin of error. So if you watch politics, they might say that the Republican, the poll has that the Republican is going to get 55% of the call, and the margin of error is 4.8%. Down here, they would say the Republican got whatever it was he got, but it's too close to call because it's within the margin of error. So that's the jargon that you'll hear being said if they're wanting to do it in the statistical way that we describe things. So you can see that you can use samples to predict what the big population could be. And the kicker in the tail is that even in this one here, let's get that out of the way now, even in this one here, oops, isn't there a 0.3% chance that you got it wrong? Okay, which means if you made 300 predictions, not that there's 300 states, but if you made 300 predictions, typically wouldn't one of them, you would have said the Republican one or whoever it was, and it was the other guy who won. And that's just life. Statistics is never 100% guaranteed. In fact, if I went down to a 95% one, which is 2 standard deviations, wouldn't I be wrong 5% of the time? In fact, if I used that standard, wouldn't I probably predict 2 states wrongly? I would predict, you know, Texas went Democrat and California went Republican. Well, I can see that happening anytime soon, but I would get it wrong twice. So I guess the moral of that story is to realize that when you are told things are true and they say it like, you know, bet your house on it, right? Sell your house and bet the money that this is going to work. You know that it's not 100% in statistics. And could you imagine they did a 90% confidence interval when they told you what was true? Or God forbid a 68. Nobody should do a 68. It just makes me cringe when I see it in the book. Do you know a 68% confidence interval is wrong 1/3 of the time? I mean, you might as well guess. Yeah, Republican's going to win. You might as well just say that, flip a coin. You're just as likely to be true, aren't you, in an interval of that degree? So 90, 95, 99, these are good numbers. The other ones are not so good. So we've covered enough of that. We did, didn't we do Canada last time? Was that our story yesterday? My pretend story about what percentage of Americans have been to Canada. So that's kind of how that group of questions work. Now we're going to look at the second group of questions. And suppose you know the population proportion P. You can use this to predict the probability of a particular sample proportion being the value that it is. Right, that's vague, so I'm going to find a question that does that to kind of show you how it works. Okay. Let's suppose AAA, you know, the guys you phone when your car breaks down or you run out of gas or whatever, right? AAA. I think it's AAA. AA is Alcoholics Anonymous. That's a totally different place, right? AAA, car breakdown place. They know that about 9% of the people who have AAA actually use it in any given year. And that's a population value, right? Because in a year, right, they know how many people are members, right? And they know how many times they get called out, so they got P. So we know a population guy. So we're going to talk about stories where we know the population P. And you can tell when it's written as P equals, that is telling it's a population parameter, right? Now, suppose there's a town. Oops, can't even write the word town today. And this town has 400 members in it. And we would like to know what's the chance that 40 of those members will use AAA. Or let's phrase it a little bit differently. The chance that 40 or more of them will use AAA. Well, I know the population guy is that. I know the standard deviation, which is PQ over N. Now, do you notice that when it's a population, it's called standard deviation? If you prefer, I'll use sigma, right? Because it's a population. And I know who P is. 0.09. I know who Q is, 0.91. And this town has 400 members, so that's essentially a sample of 400. So you can think of it as a sample. And then you put this together, you get the square root of 0.09 times 0.91, and you divide it by 400. And the answer that we get is 0.014. And P, just putting it right next to it, is that guy. And P is essentially like the mean. And I want to know what's the chances that 40 or more happen. So P hat is 40 out of 400. So my P hat is 0.1. So I'm trying to find what's the probability that P hat is bigger than 0.1. So what's the chances that I would have in this town more than 40 or more people who actually would look for help? Now, this fella is going to use the normal distribution fella. So we're going to be using salt to get the answer. Now, right in the middle is the P guy. And if I wanted to, I could do 0.01, 0.14, 0.14. I don't need to do that. All I need to do is to realize that if we call this guy here 0.1, isn't that the bit that I need? Right? Bigger than 40 out of 400, bigger than 10%. So what I now have to do is nip over to WebAssign and get it to calculate that for me. So I'm going to click on this fella. I'm going to move this across. And I'll shrink it down a little bit. And then I'll ask my question. Can you actually see salt right now? Okay, now, in the story that we've got, it's a normal distribution. The mean is basically the p-value. In this case, the p-value of the population is what we use. And the standard deviation is the standard deviation of the population. And that was the guy we calculated as 0.014. And we want a right tail, don't we? Click on it. Click on it again. Gotcha. We want a right tail, and we want to know what's the chances that it's 40 or more, which becomes greater than 0.1. And the answer is, as a decimal, 0.237 and 5 and some other stuff, which I'm just going to convert into 0.24. And we have now answered our question, which is, what's the chance that that town will actually need, will actually call on 40 or more people? It's going to happen about a quarter of the time. Now you might think, well, why would that be important? Very often these companies, these things called AAA, you probably know this. Do you know that they don't own towing companies? You know, if you break down and you phone AAA, isn't it some local towing company that comes and helps you, right? You know, it's fridsmith.co or whatever, right? They turn up. And what the AAA does is that they have contracts with people and the towing company, and they essentially book them for whatever it is, 20 trips, right? We're hiring you, we guarantee you 20. Now, if you end up having a bad predictor, and it can happen to you, do you know if you get stuck in the middle of nowhere and you're flat tire and you have to get AAA, AAA may turn around and tell you that they can't get anybody to get to you anytime soon. And the reason for that could be that the nearest towing company is too far away, but it could also be because the towing company that they've got under contract has already used up their, 21s. And they're not going to pay the higher rate because the tow company will say, well, I've given you the 20, at 15, whatever it is, 150 a shot. I've done that. If you want another one, well, I'm going to charge double. And AAA is not going to do that typically. So they can definitely make your life a misery. Do another one of these. Let's do an experiment one. I'm going to do a made up story about a new treatment. The population here is going to be the old treatment. And just made up. Imagine that they have a triple bypass operation that they use, right? So there's a certain procedure that they use for a triple bypass. And success is that the patient lives, which makes sense, right? And let's say for a triple bypass, the success rate is 70%. So 70% go in for a triple bypass, they're fine, right? Can go back to their life. And 30% die. And they sometimes put windows on it, like, if they have to be alive 6 months later, they put a kind of time window on it. Because you could be alive after the operation, right? And then die the next day. I wouldn't call that success, agreed? So they have a kind of window, whatever it is, a year, 6 months. They do it with cancer treatments as well, right? When they talk about success in a cancer treatment, they really just mean that the person's still alive 5 years later or whatever their time schedule is. Now, that is the population, right? 70% success rate. And there's a new treatment that's coming out. Maybe they use different valves. Maybe they use a different way to do the operation. But there's a new treatment out there. And they want to see whether or not this new treatment, right, is a good one. Right? So they conduct a clinical trial. And 100 random triple bypass people get to do it. Some are quite ill, some are not so bad. And they found that 73 of them were successful, right? Now, superficially, doesn't that look like the new treatment is a bit better, a little bit higher success rate? But couldn't it just be luck? When you do it, you just 100 people, you just got lucky, right? Some people die, some people don't. Could be that. So we would be interested in what's the probability that you get a p-hat, right? Which is in this case 0.73, right? What's the chances that you get that value or bigger, right? Now, what this probability is going to tell me, in fact, is that if this new treatment wasn't any better than the old treatment, what's the chances that you just get a nice answer like 73 just by, randomness and luck? Now, if that answer ends up being really small, right? So if this answer here ends up being really small, won't that be an indication that the new treatment truly is better than the old one and it wasn't luck? But if this could happen, 20% of the time, wouldn't that just be, yeah, that just natural variation? There's no real strong evidence anyway to do the new treatment. So what do I know? I know the mean, just basically the population value is 0.7. I'm about to get its standard deviation. We haven't calculated it yet. It's PQ over N. have you noticed that you always use in these questions the population value? Right. Now I'm going to do this question twice, but let's just finish this one. The standard deviation then is the square root of 0.7 times the 0.3 divided by 100. And the answer I get here is 0.046. Okay. Now I want to know what's the probability that you get a p hat greater than or equal to 0.73 using that as the mean and that is the standard deviation. So I nip back to my stalled fella. Well, I will if I can get WebAssign to behave. Right. What's your gut feeling? Do you think that 73 is big enough to be significant, or could it just be randomness and it's just a little bit bigger because half the time it is a little bit bigger, right? Any gut feelings on that one? Hard to prove, isn't it? And isn't it much better if you don't do gut feeling when you decide if a new test or a new procedure is better? Wouldn't it be better if we just rely on numbers? And that takes out the gut feeling, which isn't always accurate. Okay, so I've got a normal distribution. The mean is the population p-value, so it's 0.7. The 0.7, darn it in space, got an extra 0 there, 0.7. The standard deviation is 0.046. And we'd like to know what's the chances that we got a p hat bigger than 0.73. And I put an extra 0 in there. I don't know why I'm picking up extra zeros. There we go. And oh, dear me. The chances that that just happened by luck is about 26% of the time. That is not very convincing evidence, right? Just isn't. So you might think, well, how small does this need to be before it's convincing, right? Well, 1% would be a good number, wouldn't it? There's a 1% chance that that happened by luck, right? That's pretty small. 0.1% would be even better, right? And we do actually have standard values for these things. If you ever get into the medical world, look for a thing called the p-value. That's just a name they give to this fella here. And you'll very often find that the standard values for p-value to be significant evidence that the new treatment's better tends to be 10%, 0.1, 5%, 0.05, or 1%, 0.01. So you'll see when you read reports that this is statistically significant with a p-value of 1% or with a p-value of 5%. What they're saying is that this guy here is a very small number, and we like 1, 5, and 10. Now, I said I was going to do this question twice. Here, I would say not enough evidence. It could be the new treatment's just as bad or as good as the old one, because 26% of the time isn't this going to happen. Oh, by the way, do you know 26% of the time, this guy's going to give you an answer worse than that? Yeah, just at the other end. So what's the change? I'm only going to do one change. Imagine we did a clinical trial of 1,000 people, and the answer to p-hat was the exact same guy, right? Just for argument's sake, right? So the only thing I've changed here is that it's now 73% success rate but with a clinical trial of 1,000 people. Now, one of the good things about big sample sizes, don't you tend to get better data? So we're going to do the same P thing here. We're going to find what's the chances that you get a P hat greater than 0.73 in this world. Well, I have to change my population a little bit. Its p-value is fixed, but its standard deviation uses the size of your sample. So it's now going to be 0.7, 0.3, but now it's over 1,000. Now, can you see that's going to make that standard deviation smaller? Which is what accuracy is all about. Smaller standard deviation, less variation. So I'm going to put it in. I've got a square root. I got a 0.7, 0.3. I'm going to divide it by 1,000. And I get a 0.014. I'll make it 5 there. Now going yet again back to salt, and we're going to put that information in, and I'm 99% sure that I might get a more interesting answer out of it. Right, so our standard deviation is now going to be 0.0145. 0.0145. And I want to find what's the chances that I got bigger than 73. There. Can you see that the answer is 0.019, which I'll call 0.02, which is 2%. So the chance, what we've really found here is that the chance of that happening just by randomness is very small. So since we can say it probably wasn't randomness that was causing this, can't that then mean the new treatment is actually better success rate than the old treatment? And then what would happen in the medical world is, and this would get written in the Lancet or something, and people says, oh yeah, that's a much better way of doing what we used to do. And they will start using the new operation, or the, I don't know, maybe they use better drugs, right? Whatever it is they've now got a more successful way to do it. And this is evidence-based, right? You have data, you do a clinical trial, the clinical trial comes up with results that you then formulate into what's the percentage chance of this happening, right? In this case, by sheer accident, by sheer randomness. And if it's 1%, right, 5% or 10%, depending on the P level you're willing to accept, you now have evidence that a new treatment works. And you know, this is the exact process that is used when the FDA do a new drug. Suppose there's a new blood pressure drug out there, right? Some companies come up with a new super duper, does a better job than the old drug. They already have data on how successful the old drug is. One of the things they do is a clinical trial. Well, actually, they do other things. Do you know the first thing they do is a safety check, where they get volunteers to take the drug to see if there's any nasty side effects, you know, bad things like that. If it clears the health hurdle, they then go into clinical trials where they get 1,000 volunteers. Typically, do you know what they do with the 1,000 volunteers? They split them into 2 groups. One half gets the old treatment, the other half gets the new treatment, and then they compare them. But it's essentially this process. And if you can get significant results, right, this p-value, if it can be small enough that's significant, you now can prove to the FDA that the new drug does a better job than the old one. The old one will still be used because it's probably gone generic and it's nice and cheap. And won't the brand new one cost an arm and a leg? Well, you're too young to have it. I can tell you right now, one of the drugs I take because I'm falling apart, is $70 a month. And that's with my insurance paying 90% of it. So you know what the pharmaceutical company are charging for that 1 a month drug that I get. I get other drugs, but that's a bad one. And on the other extreme, I take a pill, a blood pressure pill, and I think it's something ridiculous like 60 cents for a month's supply. Have you ever wondered why there's such big differences between a generic drug and a brand new drug? The first drug I got is still only made by one company because it's on the, you know, the beginning stage. It's not that it costs that much to produce it, right? Why is it so expensive?
Is it because they know they can get that much for it? Like people will pay more for brand name kind of thing?
It might be. I don't know. If I could get the drug that I'm paying $70 a month for, if I could get it for a generic version for 70 cents, I'd probably get a generic version. The main reason behind it is that pharmaceutical companies, certainly they'll charge what they think they can get away with as well, but one of the reasons they charge so much is that it costs a lot of money to develop a new drug. And see, for every successful drug that they've got, they probably have 5 or 6 failures, but they spent millions on each of those 5 or 6 failures. So when they get a success, they factor in the cost of all the failures plus profit. And that is allegedly, anyway, the main reason why the prices are so high. But there are definitely pharmaceutical companies who just add a nothing to the price because they can. Right? We could do it for 100, but we'll charge 1,000. Insurance companies pay for most of it. We get plenty of profit. Which is, if you're into stocks, if you knew that a pharmaceutical company had got a really big new drug that was coming out and then successfully passed, and they know that they're going to have a big market for it, that drug company like trebles in price like overnight. And people end up getting arrested because insider trading, because somebody told them, hey guys, tomorrow we're going to do a news report on this new drug. And the minute it hits the airways, the price is going to zoom through the roof. Well, do you know what happens if people get the information before that? Don't they buy millions of dollars worth of that company? And then the price trebles. And then, 2 weeks later, they sell it and they made a big punch. Illegal. Not that you'd ever do it. But it must happen. Can you imagine you're a scientist and you work for a pharmaceutical company and you know this drug is going to work? I mean, the temptation must be great, wouldn't it? To at least tell your mum or your Uncle Joe or somebody so that they can make a few bob and maybe give you some of it. But that's why you end up in jail when you do it. Are we comfortable with this second process then? That you can use the fact that you know a population number and then use it to predict what a sample could be. You can use it to decide if a new drug is good. You can use it to decide all sorts of things. So I think what I'm going to do now, because we are getting quite close to the end, is let's just show you what those questions look like in the homework. Because Web of Science sometimes does things in its own unique way. Right now, you know about half the questions, right? Maybe a little bit more than half. Let's start you off with the question, I don't know. I'm not even sure what you see now. Are you looking at WebAssign right now? You are, okay. So I can make this, but no. Somebody said yes, somebody says.
Yeah, it went away. Now
okay, can you see it now? Okay. Right. Just talk through some of these answers. Oops, too much. Here is a population here is the N, here is the P. When they're talking about the mean, they're really meaning the p-value, right? So you just type in 0.5. As a question goes, that's so simple, it's scary, right? Because you might overthink that. Now, to get the standard deviation, won't you have to do the square root guy? And I'm just going to call it P Q divided by N, right? And you get 0.1234. So all this question is asking you to do is to take the data, right, the population and the N value, find out what the P value is, the mean, and the standard deviation. And then do it again with 2 new numbers. Then do it again with 2 new numbers, and then do it again with 2 new numbers. Do you see that's just practice at getting standard deviations? Right. Now, if we move on to question 3, P hat. So a random sample of drivers was taken in this story. Better shrink it back a bit more. Right. Saying that they never wear seatbelts. Aye, aye, aye. Bad news. So 75 out of 500. And I'm assuming here that they want answers to be in decimals. So can you imagine you just did that and you did 75 divided by 500. And you put in the answer 0.15. Now, when you're doing a standard error, why is it a standard error? Well, this is a sample, so this is P hat. So standard error, right, the sampling distributions, standard deviation, God, that's a mouthful. The standard deviation of the sampling distribution is called SE of P hat, right, that guy, right? Isn't that still going to be the square root of PQ over N, but it's going to be P hat, Q hat over N, right? So it's pretty much the same calculation, right? And there's a different P hat and there's a different fella to go with that. Here it's 700 people. The P is 0.75. The mean of this guy would be 0.57. And won't the standard deviation be that square root of PQ over root N again? And here you're going to do, oh, a 99.7. Good, guys. If you want to do a 99.7, won't be the mean plus or minus 3 standard deviations. So it's that guy. I'm going to pretend I know what the answer to this is. So won't your answer be that guy, take away 3 of these, and that guy, add 3 of these? If that was correct, which I know it's not, but wouldn't the answer be 0.27? Oops. The answer would be 0.27. And if you add 3 of those, you get 0.87. So that's basically the confidence interval questions that I did, right? Here's pretty standard question. Here's another pretty standard question. And yeah, it's the same thing. In this case, oh God, they did it. They gone and did it. I knew the buggers would. Aren't they going to do a 68% confidence interval? I knew they would do it, the buggers. Do it because they ask you, but never, ever, ever do it in real life. If you did a paper and you wrote it and you said you did a 68% confidence interval, they would laugh you out of town, right? Statisticians would look at that and say, who on earth taught that person statistics that they think a 68% confidence interval was a good idea, right? So don't do it in real life, but do it here because they tell you to. This is another confidence interval question. And we're entering the automobile one that I did. Oh, I just noticed some. I did mention it yesterday. For the test to be valid, that's basically NP. And you know that's another way of saying NQ. What was the test about NP and NQ? What did it have to be bigger than or equal to to be able to do any confidence interval or anything. It was a magic number. NP and NQ both had to be bigger than
10.
10. That's it. 10.
10.
So if that, I don't know, oh, there it is, at least 10, right? Oh, they told you there anyway, right? So you're going to find this guy, and I'm making up the numbers because I don't know what the question is. This guy's 45 and that guy's 15. Just pretend it was. Then isn't it good to keep going? Right? You can do a confidence interval. You could do anything you want. And there's an automobile story again. Another standard error, another confidence interval one. And that's about as far as you can go. So